So, last bit that I want to talk about comparing distributions on this one-dimensional data is thinking about comparing more than two distributions. All right, so lots of times we want to compare more than two distributions at once, and the South African heart data is a particular example. We can look at systolic blood pressure again for those with family with a family history of heart disease, and those without, that's 2. Those that have had coronary heart disease, and those that have not. So there's 4 different distributions we want to compare. We compare these, say, with box plots. Looking at these 2 box plots, so looking at on the left, systolic blood pressure of those that have family history of heart disease, and those that do not. So pink is healthier in this respect, that they don't have the family history. And those that have coronary heart disease, again, those that do on the right, and those that do not on the left. And the healthier being on the left. So these 2 comparisons, we're looking at coronary heart disease. Is there a difference in the distribution of the systolic blood pressure? We can talk about whether it's difference in level, that's the location, difference in scale, the spread, the symmetry, it's at a proportion above a certain value, so on. However, I'm looking at each one of these individually. And that corresponds to essentially what you were looking at in your first statistics course. Right? You're looking at testing the equality of 2 means for 2 normal samples, right? Either here or there. And so you think about what do these correspond to mathematically? What's the mathematical model that matches these pictures? Well, it's something fairly simple. So for the family history, we might have a model where we've got the systolic blood pressure on the left here, and we have an overall mean value of the systolic blood pressure, plus a change in that depending on whether you have family history or not. You might have modeled this in another way, saying that you have mu1 if you have family history and mu2 if you don't have family history. But this is kind of a convenient way to do this, that I've got an overall mean, and then whatever the difference is between the mean of those with family history and those without, compared to the overall mean, ignoring the family history. And to make this work so that I haven't got this over-parameterized, there's usually an additional constraint here that those alphas sum to 0. Okay? Has anybody not seen that model before? Has anybody seen that model before? Oh, good. I thought we were going to have a null set on both sides. So if I was going to do it now for coronary heart disease, it'd look just the same. I'll introduce another, instead of alpha, of a beta, but it's the same model, same structure of model. The parameters mean something different here. That's why they've got alphas and betas. The mu's are the same because it's the average overall. I'm ignoring that other variant. Okay? And you often assume that these residuals, the RJKs or the RIKs, were normally distributed, mean 0 and some standard deviation sigma. Each one of these models corresponds to a box plot. So when you're doing your test of hypotheses in a formal mathematical way, you'd be testing whether alpha I was 0 or alpha I equals alpha 1 equals alpha 2, etc. Right? And similar for the betas. Now, what's more interesting, of course, is to look at all of these at once. So I want to look at the folks that have no family history and no personal history of coronary heart disease. Those that have family history but no history of coronary heart disease. Those that don't have family history with coronary heart disease. Those that do have family history and coronary heart disease. Is this any different from what we saw before? Yes? No? No? How many people think no difference? Raise your hands. How many people think there is a difference? How many people don't know? No, you can't vote twice. Okay, so you think there's no difference. Why? Anybody venture a reason why there's no difference? And the difference I'm talking about is the difference between those 4 box plots, and those 4 box plots. Yes? That is the same, the scale is the same, so there's no difference. Right? Make sense? Everybody think that makes sense? Really? What's different about these box plots? Are these the same box plots we saw before? No, they're not the same box plots we saw before. Let's look back again. In this box plot, I took everybody that had no history of family heart disease and compared it to everybody that did have a history of family heart disease. This one, I took everybody that had no coronary heart disease event compared to those that did have it. Inside this group here, I have people that both have family history and do not have family history. These are different box plots. In some sense, these are marginal box plots, right? Just making one comparison. In contrast, these are having both of them. So these groups are all smaller in size because these folks had no family history and no personal coronary heart disease. When we saw the ones that had no family history before, it was this pink group plus that pink group. When we saw the ones that had no heart attack, it was these 2 grouped together versus these 2 grouped together. This is a more refined model. This is different. These are different comparisons. Which comparisons might I be interested in making? Yeah? Okay, suggest some that you think might be interesting for this data set. Try to be more precise. Okay, let me make this simpler for you. Which pairs of box plots would you like to compare? If you pick 2 box plots to compare that are interesting comparisons. Absent one and present one. So this one and this one are absent 0 and present 1. Really? Why is that interesting? So if you find a difference, what's the difference due to? One of the 2. What about your first choice here? Testing what? 4. So you're testing whether the effect of the presence or absence of family history for those individuals that have had the coronary heart disease. That's the key. So you're focusing entirely on this. If I was doing the same over here, I'd be looking at family history versus, no family history versus family history for those that have no coronary heart disease. Right? So this has been an interesting comparison for those that have no coronary heart disease. This is an interesting comparison for those that do have coronary heart disease. If I wanted to compare those with coronary heart disease, those that have no family history, compare the effect of coronary heart disease. I'd be comparing this one with that one, right? So it's a lot getting a sharp focus on that comparison so that you're holding one of these things fixed and looking at the difference. If you're trying to think, well, what is really the effect of overall of coronary heart disease, you say, well, I really would like to see what's the difference between absent 0 and absent 1. Look at that difference. And the difference between present 0 and present 1. Those together are telling you something about the effect of the coronary heart disease. Okay? This comparison of present 1 and absent 0, it's hard to know what's going on there. They're saying, okay, some of those are maybe of interest, but it's hard to say what's happening. If we were modeling this, we'd be modeling them together. So we'd have this overall mean, mu, plus an effect due to the presence or absence of family history, plus an effect due to the presence or absence of coronary heart disease. Right? And I think what you were trying to chase there by making that comparison is this guy. Some sort of interaction between the two. By modeling all of this, the comparisons become sharper. Why? Because there's less in that residual. The variation left in that residual is going to be much smaller because we've been trying to capture the variation we see in this response to systolic blood pressure and divide it up into according to which group the measurements come from. Okay? So even if we had gamma ij here equal to 0, this would still be a crisper model than those other two models together. Okay? Everybody see that? Has everyone seen a model like this before? Yes? Good. Okay, so you have to think about what these various parameters mean, what they're trying to describe. And this kind of little more complicated model is exactly that set of box plots. So again, the visualization itself has got a comparison that's of interest. It's got a model underlying it. Okay? Of course, we're not making any distributional assumptions other than the ones built into a box plot that these 4 distributions are unimodal. Okay, any questions? So, if we look at the visual comparison, oh yes, question. Why that's smaller? Principally because if there is a difference in the mean value of family history or no family history, that difference is going to show up in that parameter there. It's going to allow chase that difference. So whatever difference it takes out is coming out of the residual, right? Similarly with the beta j, any difference between the what was that? The coronary heart disease, presence or absence, and the gamma ij is something that's going, you know, you've got this difference between, this average difference between if you've got family history or not family history. You've got another average difference between coronary heart disease or not. And now, well, suppose that the difference between coronary heart disease or not depends on which group you're in, whether you have family history or not. The gamma ij is allowing you to capture a little bit of that. That's what we often call an interaction. It's an interaction between coronary heart disease and family history on the systolic blood pressure. Okay? Correct, summing over that index. Some people use dots. Yeah, so the plus means sum over that index. And those are just there because otherwise it'd have too many parameters. They wouldn't be identifiable. So, remember when we're making visual comparisons, we talked about tables, or we wanted the numbers that were important to compare to be close to each other? Same thing here with these comparisons of these distributions. We'd like the ones that are interesting comparisons to be close to one another. Okay? And so I want you to think about scanning this from left to right. We have absent 0 is easy to compare to present 0. Present 0 is easy to compare to absent 1. Absent 1 is easy to compare to present 1. Present 1 and present 0 are a little harder to compare because they're farther apart. And so in some sense, think about these different box plots as identifying this a graph where each node is a box plot. So this graph is just going from absent 0 to present 0 to absent 1 to present 1, and those are the immediate visual comparisons that you're going to make. Okay? Now, as we pointed out, some of those are of interest. Comparing that to that's of interest, comparing that to that's of interest. Comparing this to this, not so much. Right? And I would like to actually compare that pink one to that pink one, and that blue one to that blue one. I'd like it to make those comparisons as easy as possible. So I could think about a different graph. So I have every box plot as a node, and then I just draw edges between those comparisons that are of interest. Okay? And now the graph has provided me some means of saying how I should lay out my box plots. Pretty much start anywhere here and just follow the graph. Right? So if I start here at absent 0 to present 0 to absent 1, well, that's not good. That's not one I'm interested in. So that's our old version here. I want to have a new version. So I can do this with by constructing the groups in the order that I want. So I'm going to get groups. I'm going to split the systolic blood pressure by these two factors, family history or coronary heart disease or not. These are the names of the groups. And I'm just going to say, this is the order I want. I want to follow this around. Present 0, present 1, absent 0, present 0. So just following this around and display them in that order. So this display instead. So knowing what we're interested in comparing, which box plots we're interested in comparing, it suggests an obvious way to order the box plots. So I have comparison I want between heart disease or not with family history present, comparison between family history present or not when there's coronary heart, between coronary heart disease or not when there's no family history, and now between whether there's no family history or family history for those that have no coronary heart disease. You end up with one more box plot because we had to repeat this guy on the end. So we've got the immediate comparisons. But that's just a sort of a nice way to think about laying stuff out. And we can automate that. Does everybody get this picture? Does this make sense? So the comparisons of interest are right beside each other. I'm not trying to compare something here with something much farther away visually. So the way to do that is to think about a graph structure. So a graph structure here is got nodes, vertices, and edges. So we have a graph where each node corresponds to the visual of interest, the visualization of interest, a box plot or a variable or what have you. And each edge identifies a comparison. So if I have a complete graph like this, complete meaning that all edges appear between an edge appears between every pair of nodes, right? And it's undirected, it doesn't matter. I want to think about a layout is going to be some traversal of this graph. I'm going to take a walk around that graph. So that walking around following the edges is going to provide some ordering of the nodes. Okay? Does that make sense? So, for example, I could have a path that visits every node exactly once. Say starting at the top here, following down to the left from x1 to x5. Once I'm at x5, go to x2. Once I'm at x2, go down to x4 and go to x3 at the end. So this path now, this colored path, it visits every node. That's called the Hamiltonian path. Remember that from graph theory? Everybody's taking graph theory? Anyone not taking any graph theory? Okay, that's all you need to know. You've got nodes and edges, and you have paths which are just moving along the edges through some set of nodes on the graph. If that path touches every node, it's called Hamiltonian, after this Irishman Hamilton, who's talking about taking a walk. In fact, they still annually in Dublin will have the Hamiltonian walk, where you can walk around bridges across the river to see if you can get it to across every bridge. So that provides an ordering. I could continue in that way. So I stopped at x3 here, and I want to visit paths that I haven't been on before. So from here I have a choice. I could go to x5 or x2. I'm going to go up to x2. I'm at x2. There is no choice, so I'm going to go to x1. At x1 I've got a choice between x4 and x3. I'm going to go down to x3. x3, now there's no choice. I go to x5 and back to x4. Those paths together visited every edge. If it visits every edge, it has a name. It's called an Eulerian. Okay? So you just need to know what these names mean. The Hamiltonian visiting every node, the Eulerian visiting every edge. Okay? And it's a cycle if it lands back where it started. Any questions? All right, one more thing here is you'll notice that that first path that I did visited every node. And if you're paying attention, the path following it also visited every node and mopped up all of the remaining edges. When that happens, that Eulerian is a special kind of Eulerian in that it can be decomposed, taken apart into one Hamiltonian after another Hamiltonian. And so it's sometimes called the Hamiltonian decomposition. So sometimes that's possible, not always. Okay, so everybody get the ideas. So we got things that we want to order, we stick them on nodes. Comparisons that are of interest, we draw an edge between the nodes that we want to compare that are of interest. And then we find a path along that graph. If it visits every edge, then we'll see it's an Eulerian, and we'll see every comparison of interest. And the path provides an ordering. Okay? So far, so good? Okay. Right, so there's this, we're going to use now stuff that does this for you in a package called Pairviz for Pairwise Visualization. And the data that I'm going to look at is survival time from various sorts of cancers in different organs. Survival times, I believe, in days of individuals who have cancer in particular organs. And there's only 5 organs that are in the data set: breast, bronchus, colon, ovary, stomach. So we're looking at survival times in days. So there's a data set called cancer. So I'm going to split out the organs. These are going to be my groups. It's just, again, with cancer splitting to the survival based on organ. So these organs now are going to have survival times for each of the 5 different locations for cancer. Okay? So there are 5 of these things. Each organ is going to be a node. And in Pairwise it has, that's why you need to know the names. You can ask for the Eulerian on a complete graph of 5 nodes. So Eulerian 5 is going to produce this ordering, 1, 2, 3, 1, 4, 2, 5, 3, 4, 5, 1. And you'll notice that 2, for example, is beside 1 and beside 3 and beside 4 and beside 5. 3 is beside 4 and beside 5 and beside 1 and beside 2. Every pair appears. Okay? Every pair appears in that order. And that allows me to create some box plots. So I'm going to get some colors here, 5 different colors corresponding to the different organs. And then I'm going to call a box plot on just organs. Use that order, which means some of them will be repeated. Right? The first box plot will be on the first organ, the next on the second, and the first box plot, the first organ will appear again in the fourth, as the fourth box plot. So we do that, we get that. And so now visually we have pink is the same cancer. This green is the same cancer, this blue is the same cancer, purple and that sort of olive green also. And we have every pairwise comparison appearing right beside each other. Going breast, bronchus, colon, breast, ovary. So breast to bronchus can be compared there, colon to breast, breast to ovary, and the last one, breast to stomach here in survival times. All right? And I'm going to just take the square root, since they're skewed out like that with long survival times. I can take the square root of these and just do that again. So there's what it looks like for square root of survival time. Make these things a little more symmetric looking. Okay? Any questions? So just getting that Eulerian says, okay, you get all of the pairwise comparisons in one plot, which works pretty well for small numbers like 5 anyway. Another thing to notice is that you don't see in the first 5 comparisons here, first 5 organs here, you don't see all colors. You're missing the purple from here, and the pink has appeared twice. So this is an Eulerian, but this first part is not Hamiltonian. If it was Hamiltonian, you'd see all 5 organs appearing in the first part. Okay? So you have 2 pinks in the first part, and you've got 2 purples in the last part. So we could get Hamiltonians with, in Pairwise with this H paths. Gets a Hamiltonian decomposition, which will give you one Hamiltonian followed by another Hamiltonian. So all 5 numbers appear in each row. And I get them in one solid vector here by just saying matrix equals false. And now do the same plot I had before, just use this order. And now this order has the virtue of all of the comparisons are there beside each other, and you see in the first 5 you'll see all 5 organs, and in the last 5 you'll see all 5 organs. And breast appears 3 times just to make all comparisons appear to get the cycle to finish. Okay? So you can get all pairwise orderings, and you can do that in lots of different ways. I've just shown you 2. Some Eulerian, and this is another Eulerian, but it's composed of 2 back-to-back Hamiltonians. Any questions? Yes? It's not random, but it's certainly not paying very much attention. It's not any particular order. We might like a better order, right? We might prefer to have things that matter appear closer on the left, right? The first things you're going to look at. Particularly if instead of 5, I had 15 or 35, something like this. Maybe I don't want to look at all of them, but I want to look at all the important ones. So think about how you might do that. Well, we have this graph where we got the nodes correspond to the box plots, or in this case, the organs that are of interest in comparing. And we're so far interested in all comparisons. But we could use some stuff that you know about. You know, for example, how to test the equality of means between two samples, right? So you could do a t-test on that and get the significance level. And you could do that for every pair. So you could test all pairs of organs, all pairs of samples, get the p-value for all of those, right? The ones that have the smallest p-value, suggesting the biggest differences, most significant differences, maybe those are the more important ones. Okay? So there's a test in R that will accomplish that for you called the Pairwise T-Test. It has the virtue of not just doing all pairs, but also making some adjustment to the significance level, the p-value, to take into account that you're doing multiple tests, doing lots and lots of tests, right? To try and make that p-value a little more honest. For us, it doesn't matter, because we're just using the order. It doesn't matter if it's perfectly correct, as long as it maintains the same order, right? And again, this is a t-test, which is testing means at making assumptions that the standard deviations are the same. And we're looking at box plots. Box plots are going to show all kinds of different departures between those two samples than just the mean values. So we're going to use this as a rough and ready thing. So I'm going to take all of these p-values. So here in this matrix, the p-value comparing square root of survival time for those with breast cancer compared to those with bronchial cancer. It's 0.00024. That looks very significant. Comparing ovary to breast, that doesn't look like it's that different. 0.075 is the p-value associated with it. We would say no difference in those two. Not nearly as interesting. So what I'm going to do is think about take those p-values and give those to the edges, because the edges are the comparisons. So I have a p-value on every one of these edges, and it could be a p-value, but it could be any other measure of interest between those two nodes. And now I think I don't just want a Hamiltonian on that. I may want a Hamiltonian that has the smallest p-values. Maybe the smallest sum of p-values. Anybody recognize that problem? If I was looking at a path here that reached every node whose sum of weights was as small as possible. Yeah? Traveling salesman problem. Right? So you could solve a traveling salesman problem here. Or use a heuristic to try and solve that traveling salesman problem and get yourself a Hamiltonian that's got some pretty significant ones on it. Alternatively, I could just be greedy and say I want an Eulerian, but I want to find the value that has the smallest p-value first, and then from either end find the next smallest p-value, and the next smallest until I've mopped up all of the edges. Okay? So, need to pick up where we left off last day, and last day we were looking at comparing several distributions at once. And you recall that we were using graph structure to describe which comparisons were of interest and which were not. And we had introduced some graph theory basic concepts, graphs being objects that have vertices and edges, connecting vertices. And then they have paths that follow the edges on that graph, cycles if they return to the point of origin. And we talked about Hamiltonian paths or cycles, Eulerian paths or cycles. Any questions on that material? Particularly from those that have not seen any graph theory before. So it's just going to be a convenient way to order some things. And so when we look at Eulerians, remember Eulerians visit every edge in the graph, Hamiltonians visit every node. And so we may be interested in seeing every box plot appear here so that every pairwise comparison appears. So that means we're going to be following an Eulerian path on the complete graph whose nodes are the box plots. Okay. And finished last day looking at, we could do T-tests, for example, for every pair of samples. In this case, every pair of organs that we're looking at in this data set, this square root of survival times, and get the p-value associated with that. And with a little bit of work, which is just turning that into a symmetric matrix, we can apply the p-values to the edges. Those are edge weights, and now use those to choose some paths as being more interesting than others. Particularly those edges that have small significance levels are the ones where there's the greatest difference between those two organs in terms of survival rate for cancer there. Okay? So those are kind of interesting. So a little work, we can put those weights on, getting a symmetric matrix of weights. And this Pairwise package then allows us to find an ordering, beginning, for example, from the lowest p-value, that is the most significant comparison, to the next one from there on in a greedy fashion. So it's the next best available, the lowest weight, the edge having the lowest weight of all those edges that have not yet been visited from that node. Okay? So this is suggesting a particular ordering if we're going from the lowest significance levels to the highest significance levels, and going the other way around by just taking minus the weights. We did here as well, you could have a Hamiltonian decomposition, in which case we're going to have our Eulerian is going to be built out of Hamiltonian. So the first row is a Hamiltonian, second row is a Hamiltonian. That first row is actually picked to be the one that has the lowest values. So a traveling salesman problem is being solved to pick that first Hamiltonian, and then the next ones, etc. Okay? So you can get fairly complicated. So here's our Eulerian, just using the low to high Eulerian. And you can see that you don't have a Hamiltonian because you don't have all 5 colors in the first 5 pictures here. Right? You've got this olive green is repeated. And looking at the Hamiltonian with the lowest total weight is going to try to produce every pair there is going to be try to make that as significant as possible. So you can see as big a difference as possible as measured by that significance level for the pairwise comparison. It's trying to do that, but it has the constraint that all 5 of these have to appear. And so you don't see this comparison, this breast versus the bronchus necessarily appearing beside each other, because this particular Hamiltonian is going to give you the smallest total sets of total sum of the significance levels. Okay? So it's not by any means perfect, but it's a nice automatic way to lay out those box plots. Any questions? And that's doing the high to low, so these are the least significant that are appearing here beside each other. Okay, so that's where we ended last time, and we're looking at ordering on that complete graph. But we need not use the whole graph. If there are only some bits of it are interesting, we just use those pieces itself. So we need to have some way of making graphs and manipulating graphs. And in the Pairwise package, there's something that'll make the complete graph itself, and you can plot the complete graph. And also we can have subgraphs. So for here, for example, I'm going to get the weights that we have according to those significance levels. I'm going to get the median value, the 0.5 quantile of those weights, get the median one. So I just want the upper half that are most significant, which means the half that have lowest weights. So instead of that complete graph, I'm going to take the subgraph, and these are the edges that have the smallest significance levels. Okay, so said I'm not interested in all the comparison, but just give me the ones that are really significant by that t-test. Okay? And just a little bit of manipulation in R here just to trim those out. So if you have that, then you want to say, well, maybe I want to traverse this graph in my layout. I don't want to be making comparison between breast and ovary or stomach and bronchus or ovary and colon, etc. But just these, I want to see the significant comparisons, which amounts to traversing this graph. Everybody with me? Okay. So I can ask for an Eulerian, like I did before when I just gave that argument as a number here, that assumed it was a complete graph. Now I'm giving it the actual graph structure and say, give me the Eulerian on that graph. Okay. Now, to be guaranteed an Eulerian, you need to have a so-called even graph. And an even graph is where the number of edges at every node is even, which means if you go into a node, you can get out of it again. Okay? Because if you don't have an even graph, you may be in a place where you get to a node and there's no edge out that you haven't already visited. Now, for this particular graph, it's not even, right? So stomach has degree 2, it has 2 edges. Ovary has degree 2, has 2 edges. Bronchus 2. Breast has degree 3, not an even number. So it has 3 edges coming out, and colon has only 1 edge connecting at the breast, and that's, again, not an even number. However, it's not hard to see that I could actually travel and visit every edge for this particular graph, provided I start over here at colon without introducing any new edges. Okay? So if you have an even graph, it's guaranteed you can get an Eulerian, but if you don't, sometimes an Eulerian still exists. So we have an Eulerian here, which goes, this one is trying to, this function here cannot do what we see immediately here, because that becomes a very difficult problem to find. Always be guaranteed to get an Eulerian that's minimal length. But it's going to add edges to make things even. So we need to add an edge, right, to get things even. So it's going to go from bronchus to breast to colon to breast. So it's added another edge. Adding that one edge, having 2 edges between breast and colon, made the breast have degree 4 and the colon node have degree 2. So it becomes an even graph. So what's happening in this particular package is it's going to add edges, which means you'll have redundant edges being visited just to get an even graph, even though you and I can see that there is no Eulerian here from this simple graph, which doesn't have that. Okay? So bronchus, breast, colon, breast, then stomach, ovary, bronchus. So 'cause it happens to start here, it goes there, there, back. Okay? Everybody see that? So that's the importance of an even graph. Finding a Hamiltonian for any graph G, any arbitrary graph, is hard. So there's no function that solves that problem. And luckily for this particular graph, there are only 2 solutions, and they're both obvious and interchangeable, which again we can just write down, as we saw here: colon, breast, stomach, ovary, bronchus, back to breast. We visit them all. That's going to give us a Hamiltonian, and for this graph, an Eulerian. So that's just viewing it and writing it out by hand. Okay, so I can use that graph and do a greedy Eulerian on that graph, and you can see I'm going bronchus, breast, colon, breast, stomach, ovary. Now, all of these pairwise comparisons, the guys that are adjacent to each other, are significant according to a t-test. And so, in some sense, by taking the top half or the most significant edges, we've got a display that's just saying, just show me the stuff that matters. Show me the box plots that matter. Those are the differences. I can see them immediately beside each other that these are significant. So this comparison between in here, the olive green and the bright green, the Kelly green, have higher, or they're in the higher half of the significance levels of all those that are available. That's why they don't appear beside each other. Okay? So, what's cool about this? Well, what's cool about it is that if you can have some means of getting a graph that's telling you what are the interesting comparisons, you can think about how might I traverse that. Say, at least in a greedy Eulerian fashion, that you visit every edge. You may have to visit some edges more than once, just to make sure you visit all edges at least once. Okay? So this is the Hamiltonian order that we saw there, starting with colon, breast, stomach, etc. We still see all of those comparisons with fewer plots. Here we had 7 box plots. Now we only need 6. Okay, so it's a little tidier. It's because of that extra edge we added. All right, for the South African heart data, we had particular comparisons that were of interest. Right, given that the family history is absent, you want to compare those folks that have had coronary heart disease and those that do not. Right, so it's going to be present 1 versus present 0, or absent 1 versus absent 0, or absent 1 versus present 1, right? So you're going to be changing one of those at a time. So we can, in fact, say, I'm going to make a graph object, this graph nil, with nodes given by these names, and make it undirected, and then just add all the edges that I'm interested in. So you can actually build the graph up from the bottom if you have things that you know you're interested in. Right, so when we're looking at the survival rates from the various cancers in those different organs, we're looking at some automatic way of finding the interesting ones. This one we know which ones we are interested in, so we can build that graph by hand. So we add the edges where we think they're interesting, and then get the Eulerian on that graph. So we have all pairwise comparisons, we visited all edges. And so now, sooner than those original box plots that we looked at when we first looked at this data, this is suggesting exactly the comparisons that we want to make, just going around this circle, and those are the box plots, so they're right beside each other. With, of course, one extra box plot because it's a cycle. We've gone back to wherever we started from. Okay? Does that make sense? Any questions? So you can do all this stuff. Important thing is that it makes sense, that you can get the concepts here. You can look at the code at your leisure to see how it's actually accomplished. So, some summary here. We're operating on the fact that pairwise comparisons are often best made when the displays are beside each other. That's good. That's the best way, having nearby objects. Having objects be nearby, be the ones that you want to actually make the comparisons between. A graph structure allows you to think about who should be nearby each other, right? Which nodes should be nearby each other. So you have nodes, which are the displays, the thing you're going to display, and the edges say which pairs of displays should be adjacent. Graph theory things, Eulerian paths, Hamiltonian paths, give you information about how to select. Make sure you see all pairwise comparisons, or you see all of the all of the displays in a smaller configuration. Weights can allow you to choose between which pairs are more interesting, and of course you can also build your own graphs if you've got some sense of what is important beforehand. That's all was going to depend upon the context of the problem. Okay? So this Pairwise package allows you to do a lot of this stuff, and that's very handy for laying out displays. I should point out that this is not peculiar to box plots. Obviously, we could have had anything here, densities, whatever you like. It's also not peculiar to comparing distributions. This is just when I want to order displays. It's not necessarily a spatial layout of the display. I may want to order this in time. So I see one display and then the next display. So I see them one after another. It's any way of ordering displays. Okay? Any questions? None? I think that's the last slide. Yep.